phenomenal hot springs.
Good deal. Well, that'd be nice.
Yeah, I don't know how they gave you the hall pass, but she's.
You got kids for the weekend?
I'll be back that day. The movie night tomorrow night. It's just a little overnighter.
Nice.
But yes.
Movie night tomorrow night. You watching Dune?
Huh?
Dune's coming out tomorrow night.
Oh, is it? We got a 4-year-old. It's hard to get in past the animation. Anything beyond it, even in the world of animation, it can it's very very limited.
You might.
So like heavy metal.
Yeah,
We talked. I started mine on heavy metal pretty early. They do okay with it.
Like 10 when I saw it.
My voice already got issues. I can't give more issues.
Like 8 when I saw Akira.
I won't look at females the same way anymore.
Yeah. I think mine are about ready for. I think they're about ready for Lord of the Rings.
Wow.
Dune might be a little bit of a stretch, but my son's really into fantasy stuff right now, and orcs and goblins and stuff like that.
Is it
So.
Bakshi? Like, was it Bakshi? Did the animated?
Oh, there's that option. I hadn't thought about that. There's the old cartoon Hobbit from the late 80s, early 90s, probably.
It was in some like maybe late 70s.
Really?
Yeah.
I remember watching those as a kid.
So we're currently reading the Lion Witch Logo series by C.S. Lewis. And what I didn't know was he and J.R.R. Tolkien used to be part of this poets club. Hit the pub, exchange stories, and they did this for forever.
Mm-hmm.
I didn't know there was a connection between those two.
Yeah, it's same. They're both doing a lot of their writing in the UK based on a lot of Northern European folklore and around the same time period. And both I'm trying to think of what who's the philosopher that don't mix up should with is. You can't should and is or something. I think it's Kierkegaard. They're both heavily influenced by Kierkegaard. There's a whole collective of people in the UK at that time that were doing a lot of writing. It was sort of the anti-James Joyce movement of the realism movement of the time from Europe. I came across this the other day. IUPAC was founded in 1919. Chemists in 1918 confused Unga Bunga. What did they do before they had the IUPAC rules? They just made shit up, which is why there's so many weird names out there. That wasn't that long ago. All right, let's do some practice with chair conformers and cyclohexane. We're going to spend most of today talking about what happens if it's not all hydrogens on the cyclohexanes. What does that do to the different conformers?
Very well read.
So remember your tricks for drawing cyclohexane. Start with two parallel lines that are offset just a little bit from each other. Then draw a V that connects them. And your scale might not be perfect every time, but that's okay. People that are used to organic chemistry will at least know what they're looking at here. And then if we want to add a substituent to this, we could go through and we could draw all the possible places that you could have something added. So remember, if this is really, if we're looking at it sideways, then this front section is sticking out towards us. I'm going to draw it a little bit bigger, so you guys don't need to do this for the sake of answering this question, but just to help you see visually, since we're still getting used to this. So we're looking at the side of cyclohexane on the edge, and I'm going to grab Brad a set of molecular models. You guys might want to grab your molecular models for the sake of being able to see this. Add a isopropyl group to it. How are your hands, Brad?
What?
How are your hands?
Good enough.
Nice. All right, so a reminder that when we say the chair conformers, we're talking about this shape that allows it to avoid all those torsional interactions so that all your hydrogens can be in staggered conformers. And remember that we have two classifications for all of the hydrogens that are attached to cyclohexane. They're either going to be axial, meaning pointed straight up and down, or relatively close to straight up and down from the ring structure, or they're going to be equatorial, sticking out from the ring structure. And so, if we're going through and we're going to label all of those, this carbon has a bond going away from you and a bond coming towards us, so the other two bonds have to be pointed away from that and are going to be flat relative to the plane of the board. They're going to be parallel to the plane of the board. This front carbon already has one bond that's parallel to the plane of the board. Even if it's in front of the board, it's still parallel to the board. So a bond that's like this, and it's got one bond going away from the carbon into the board. So that means there's going to be another carbon coming out, or hydrogen sticking out further, and one that's going to be sticking basically straight up. Right, so here we have the equatorial was one pointing away from everything, the axial is the one pointing perpendicular to, if you picture the ring being flattened out, it's then the axial hydrogens, the ones that are going to be pointed perpendicular to the plane of the ring, perpendicular to these four carbons. So these four carbons will always make up a plane, right? And axial means perpendicular to that. Equatorial means more or less parallel to the plane that these four carbons make up. Right, so every carbon is going to have one axial and one equatorial position. And I'm overemphasizing how big this bond is to show that it came out from the plane of the board and then it's coming out further. And so every carbon has these two positions, axial and equatorial. The two different chair conformers of cyclohexane, of methyl ethyl cyclohexane, are going to be, there's going to be one conformer that puts the isopropyl group in an axial position, and one conformer that puts it in a equatorial position. Because remember, all of these carbons, despite the fact that we draw it as having a head and these four that are in the middle and a footrest, they're all identical when you go around and look at your cyclohexane when you have it built. They all wind up being identical. You can take any carbon and make it the headrest, or you take any carbon and make it the footrest. And so they're all identical. We just draw it like this and define a headrest and a footrest out of convenience. So we can put, so if all of these carbons are identical, the only difference between the two places we could put the isopropyl group is it axial or is it equatorial? All right, so I'm going to clean this up. So we're going back to skeletal structure, so we're going to only be looking at the carbons here, but remember the hydrogens are still there. So we can have an isopropyl group that's in an axial position, where it's perpendicular to the plane of the ring structure. And if we flip that down, and the head and what was the footrest and flip it up, we wind up with everything switching positions. Thank you. Let's see. Again, you guys don't need to make the front part any bigger, but for the sake of helping you visualize it right now. So we flipped everything, we flipped this part down. The hydrogen that was here and was printed in the equatorial position is now pointed down in the axial position, which means that your isopropyl group, your methyl ethyl group, is pointed in the equatorial position or direction. And so those are your two conformers here. And it's going to be the same for anything, any cyclohexane that is mono-substituted, that only has one thing attached to it, one branch. Regardless of what that branch is, it can be in one of two positions, axial or equatorial. All right, so questions so far?
I'm guessing it's more complicated constituents.
Yes and no. There's one main thing to look at. It's a lot like drawing those Newman projections where we were just trying to say, okay, I'm going to put the biggest groups away from each other. Mainly what we're going to be doing here is we want the biggest groups not in an axial position. So remember, when you look at those axial positions on your model, the axial positions are the ones that are pointed straight down or up. So if you're in a chair conformer, it's the ones that are holding the chair up. And if you look at it, if something's in an axial position, it winds up pointing in roughly the same direction as the axial substituents on the carbons that are one carbon away from it. So in this case, in addition to having this equatorial hydrogen here, we have an axial here and an axial here. That are kind of pointed towards the isopropyl group. And if that's the case, they're going to sort of bump into each other. You're going to have some steric interactions there that are not very favorable. And so we wind up, if it's just a methyl group that we put on there, methyl group's pretty small. We talked about that a little bit on Tuesday. Just putting a methyl group on there, you wind up with a 95, so what, 19-to-1 ratio, roughly, where if you picked any methyl cyclohexane at random, there's a 95% chance it'll be in the configuration that puts the methyl group in the equatorial position. All right, so if you have your methyl, Brad.
So would the cyclohexane chair look be similar to this? I don't know if you can see that.
You're close.
Sure.
So that's a boat configuration. So if you take that, you can put one of those corners up like that,
And one down.
and one down. So see how that looks kind of vaguely similar to what we have there?
Okay, and then the other one would be both.
And the boat would be, you have both points that way, the way you had it. And so if it's a monosubstituted cyclohexane, it's basically that simple. It's more stable with your substituent in the equatorial position because you avoid what they call 1,3 diaxial interactions, which is just a fancy way of saying sterics. Things bump into each other and push each other away. Right? It's just it's a very specific version of sterics where, and it's 1,3 diaxial because if you call this carbon 1, carbon 3 is over here. And so it's the carbon 1 to carbon 3 axials are interfering with each other. Because the axial position on carbon 2 is pointed away from your substituent, so it doesn't make a difference. It's specifically looking at carbon 1 and carbon 3 and carbon 5, really. And we're always just going to try to minimize those interactions. So if we go back to looking at butane, look at the Newman projection for butane, we saw that there was that gauche interaction when we put these two methyl groups, if we put them in the gauche position, meaning staggered but adjacent to each other, there was that they kind of pushed on each other. And if we have cyclohexane and we're looking down these two bonds, we're looking along these two bonds here in this Newman projection, you wind up with something really similar, where carbon 3 is interacting with carbon 1. And if we're in a cyclohexane, it can't just freely rotate to be apart from each other. The only way you can get rid of that gauche interaction is by doing a chair flip, by going from your isopropyl in an axial position to an equatorial position, because in an equatorial position, those interactions don't occur. So if you have cyclohexane with a substituent on it, even just a methyl attached in one of the positions, take a second, get it set up that way so you can see what these interactions look like, and then have it go through a chair flip. So you don't even need to go to the trouble of adding all the hydrogens to your methyl group. Just put a methyl group on, or put a carbon on there. And you can definitely see, even I'm going to put the hydrogens on my methyl, on just a methyl group, not even an isopropyl group, just so you can see visually, hopefully, what we're looking at. when you have these big, bulky groups like a methyl, and you wind up with them pointed in an axial position, they bump into each other like we were just talking about. So axial, axial, bumping into the methyl, that's that 1-3 interaction. Physically, you're just trying to be in the same place at the same time. But if you do a chair flip, if you take this and you flip it into the boat conformation is still not all that stable because you wind up with these hydrogens bumping into each other. But at the very least, as soon as you do that, your methyl group is pointed away from everything else. And you look at the other chair conformer, now all of a sudden, you don't have those same interactions. Those 1-3 diaxial interactions disappear the second you put your big bulky group into an equatorial position instead of axial. And the second you flip it back the other way again, you wind up with them bumping into each other. All right, so that's why we have, this is an equilibrium reaction because we do have a possibility of it flipping into that, into the axial position, but it's going to favor the conformer that keeps the big substituents in equatorial positions. So if we look at the same, graph, once we put it into the equatorial position, now that puts this ring structure in our methyl group, we're actually in the anti-position, to use our Newman projection language. They're completely opposite of each other. So this is modifying the whole idea of the Newman projections and twisting things around and rotating things so that the big stuff is opposite of each other, but it's the same idea. We just talk about it in terms of cyclohexane and ring structures. We talk about it in terms of equatorial versus axial, because it's a convenient shorthand rather than having to draw this every time. Right?
This position right here on the board is more favored
Correct.
because they're offset from each other.
Exactly. And you can see how these hydrogens that are pointed up that are parallel to each other more or less, one of these hydrogens is going to be in that position as well. Those are the axial positions. And by putting in equatorial, it's not right here, bumping into the other one. The bigger, as you might expect, the bigger the substituent we put on there, the more that affects. So when it was a methyl group, it was 95 to 5%, right? It favored having the methyl group in the equatorial position, but 1 in 20 is still a pretty good odds of finding it in the less favorable position. If you make it a bigger group, like a T-butyl group, or a dimethyl ethyl group, the ratio goes 99.99% will sit in that in that equatorial position. And only 0.101% of the time will you find it with that big group in the axial position, right? The bigger the group is, the more the equilibrium is going to favor keeping it in the equatorial position. And we can see that, and we can actually put numbers, energies, to those interactions as well. If you put a chlorine on there, it has 1,3 diaxial interactions. But only 2 kilojoules per mole. A chlorine is not as big as a methyl. So those 1,3 diaxial interactions are not as significant. So you get a 70-30 ratio. Make it an OH, it's a little bit bigger. Make it a methyl, it's a little bit bigger. Make it an isopropyl, and we're looking at 9.2 kilojoules per mole. And that's 97 of the time is it going to favor keeping the isopropyl in the equatorial position. And you might notice that this is not a linear relationship, right? We're talking about changing delta G for the reaction. There's a, this reaction, axial to equatorial, has a potential energy surface, right, that looks like that. And the difference, the change in energy from products or reactants to products, governs its equilibrium, and that has that familiar, I'm going to keep harping on it because it's a really kind of a big deal when it comes to an exponential difference, exponential relationship between delta G and equilibrium constant. Your equilibrium constant, it's always going to be equal to E to the negative delta G over RT. That R, that's the universal gas constant R. In energy units. But so as you change delta G, as you make this difference bigger, K is going to get bigger and bigger exponentially, which means your ratio is going to get bigger exponentially.
Is that because delta G in this case would be negative?
Delta G is negative, and so if you're making it more negative, the bigger your bulky group is. The bigger this interaction is, the more it favors having it in the equatorial position. Because this is relative to having it in the equatorial position for all of these. Right, so the bigger your group is, the more negative delta G is, the bigger your equilibrium constant gets in that exponential relationship. It also does tell us that temperature plays a role, right? If you change temperature, you can dramatically change equilibrium constants. Because T is also, it's a weird relationship. It's not a pure exponential relationship, right? Because it's in the exponent, but there's a negative and it's 1 over T. So if you flip all that around in your head, increasing temperature will make this whole term smaller, which could either make it closer to zero, it'll make it closer to zero no matter what, but it could make it less positive or less negative depending on what sign delta G has. Right, so temperature is a complicated one to work back. It's not as simple as saying, oh, increase temperature, increase K. It depends what delta G is. But we can absolutely say that the more negative delta G is, the more we're going to favor the products with an exponential relationship. All right, so what do we do if we have more than one thing attached? Well, a few things are different. For starters, we can't just specify what carbon something's attached to anymore. Because if we have a ring structure involved, all of a sudden we can't freely rotate anymore, right? If we cannot freely rotate anymore, then we can't really change where these are relative to each other. We don't have the ability to just flip this around without breaking the entire ring structure, right? So having more than one thing attached to a cycloalkane means we have to consider what's called stereochemistry. It's called stereochemistry because originally it meant there were two options. Stereo, like hearing things in stereo versus mono. If you have two options, in this case, you can either have your two methyls on the same side of the ring or on opposite sides of the ring, while still having them on carbon 1 and carbon 2. So this is what's referred to as as a cis-trans isomer. Cis meaning same, trans meaning across or change. If you go across the ring, in order to get from one substituent to the other substituent, it's a trans isomer. If your two isomer, or if your two methyl groups are on the same side of the ring, we call it a cis isomer. Yeah.
Would it be able to rotate which side of the ring it's on by itself? If it doesn't change the carbon it's attached to?
So this one, we could take this, if you picture the cyclohexane, flip it like a pancake, you could get the same molecule that had both of them on the bottom, right? So yes, we can flip around whether they're both on top or both on bottom. Turns out that's a more complicated question when you look when it's trans. Because if you took this and flipped it like a pancake, you get the same thing. So in this case, it does matter which one points up and which one points down, because there's no way that you can make this carbon go right there, or put a methyl group right there, and the other methyl group over there. So we'll get into non-superimposable mirror images, is what that type of stereochemistry is called, or enantiomers, which basically it's like your right hand versus your left hand. They're both identical except for the fact that they're flipped, right? You can't put your right hand into a left-handed glove. So we're going to start by just looking at the idea of cis versus trans and not worry about the mirror image aspect of it for right now. And we'll get to that soon enough. Maybe by the end of lecture, actually, now that I think about it. So this also adds a wrinkle when it comes to naming these, because these are different molecules, despite the fact that they're both 1,2 dimethyl cyclohexane. You can't get from this cis 1,2 dimethyl cyclohexane to the trans 1,2 dimethyl cyclohexane without breaking bonds. Right? So if I have a cis version that I built here, without pulling off hydrogens and carbons and switching them around, there's no way I can make this look like the trans form. Which is why they're two separate compounds. They will actually have two different boiling points.
Is that because the methyl group would be too big to like rotate through it to switch sides? Does that make sense? Like if
so I see what you're saying. So you could conceivably rotate this through the ring,
yeah.
but the sterics are going to be against that, right? You're going to basically have to break one of these bonds to allow it to do that. Right, so if I tried to take this and go, I can maybe do it with the models because they're not perfect. But even with the models, I can't really do it. You wind up with it. You have to break something in order to do that. So I could, if I broke this bond, then I could come in here and reposition things and put it back to being trans. But I have to break a bond to do it, which makes it two different compounds.
Yeah, it requires energy.
And that requires a lot of energy, more energy that we have at room temperature, normal temperatures usually. All this goes out the window when we get to high energy systems, when you get to things like, the surface of the sun. If you look at a plasma, which is when you get to super high temperatures and high pressures, plasma, the official definition of a plasma is that the electrons have enough energy, kinetic energy, that they're not bound to nuclei anymore. Which means all of our ideas of covalent bonding go out the window. There is no covalent bonding in a plasma. So this is sort of we'll call it an Earth-centric view. It works for anything up until you get about as hot as Venus. And even Venus still has covalent bonds, but they're easier to break and it's an inhospitable enough place for covalent bonds that they break pretty easily. All right. Is one of these stereoisomers going to be more stable than the other? Probably. How can we tell which one is more stable? Sterics. Yeah. Just like I tell all my Gen Chem students, if anybody asks you why something happens in chemistry, electrons is never the wrong answer. Sterics and electronegativity in OChem. You can always tie it back to one of those two things. Those are the two main things that change things. We're not dealing with electronegativity yet because everything's just carbon and hydrogen. But yeah, so if we wanted to look at which of these was going to be more stable, let's try drawing our chair conformer for both of these and see if one of them winds up being significantly more stable than the other. This is where it can be useful to use Me for methyl or CH3 rather than just leaving a skeletal structure because it reminds you it's bigger than the hydrogens. So if we have cis dimethyl, so remember on this position or in this carbon 2, we have two positions as well. We have equatorials coming out towards you, and axial is pointed straight downward. So basically what we have here, if you add another methyl group here, is if this methyl group is pointed straight up, this methyl group, if it's cis, this methyl group is going to be pointed in the equatorial position. Right, because if you can picture taking this and flattening it out to make it look like a flat ring again, the two hydrogens would both be pointed downward and both methyls would be pointed upward. So if I just take this and rotate it so it was totally flat, I'm only going to draw part of it here. We just took that, flipped it down. Our methyl is pointed above the ring, our hydrogen pointed down, and here we're going to wind up with our methyl pointed, it's going to be hard to draw, like up and coming towards us, and our hydrogen down and coming towards us. Right, so if I take this and make it try to make it totally flat, which it doesn't like to do because the bond angles aren't right, we wind up with something like that. So we have one axial and one equatorial. Is the other conformer going to be more stable? If we took this one and did a chair flip, the one that was axial is now going to be equatorial. But we flipped this position too, right? So we want from one methyl being axial and one equatorial. And which of those is more stable, axial or equatorial? Equatorial. So we had one axial, one equatorial, so one favorable, one unfavorable. And when we flipped it, we got one favorable, one unfavorable. So in other words, if you have one axial and one equatorial, when you do the chair flip, you still wind up with one axial and one equatorial. So one favorable, one unfavorable. What if we took this cis and made it into a trans? If we took this and we switched it, let's leave the top one where it is. I'll redraw that bond I just erased. If we have our two methyls on opposite sides of the ring, right now they're both axial, right? They're both unfavorable. But what happens when we flip it? We go from both axial to both equatorial. So both unfavorable to both favorable. So if we want to know which stereoisomer is more stable, we basically tally up what the different conformers have. Is there a way that I can have everything in an equatorial position? If so, that's going to be more favorable. If there's no way that you could have them all in an equatorial position, that's going to be less favorable. Because no matter what you do, you're going to wind up for this cis isomer, you're going to wind up with one axial and one equatorial no matter what. So the 1,2 trans isomer has both the least favorable conformer and the most favorable conformer. But this is what matters. If we're talking about which stereoisomer as a whole is more stable, we look at this when we tally up favorable and unfavorable interactions. Right, and so to see the difference, you might want to switch your structure around. So if you had the 1,2 trans, so everybody see when I switch it, now it's trans because the two carbons are on opposite sides of the ring structure, not pointed on the same side of the ring structure. And if I start with, there we go. So they're both in the axial position right now because you got this carbon pointed the same direction as these two hydrogens. This carbon pointed in the same direction as these two hydrogens, so less favorable. But if I do a chair flip, now both carbons are equatorial. Now they're both pointed away from everything else. Right, so drawing it's helpful once you're used to how to visualize it. But until you get into the habit of being able to look at this and know what's an axial position and what's an equatorial position, it's kind of hard to know just by looking at the drawn structures. All right, so the slides walk through how you could draw both of these. Let's take a break. And then we're going to look at a different possibility. We'll go through that same process with a different stereoisomer where it's not 1,2, and look at what the possibilities are. So you get some practice with that. So let's come back at 5 till, and we'll start doing some practice with. We'll do say 1,3 dimethyl. Okay.
Any comments? Did you not bring your group?
No, I didn't do that. Let's create some carbon footprint waste.
Smoke free.
Yeah, of the freaking easy approach. Convenience is.
So when when the sterics say that the atoms are pushing each other away, it's the protons that are interacting in that instance, right? It's not the electrons, right?
Flip that. Because the protons are stuck in the nucleus, right? The nucleus is tiny.
Okay. So if the element was, say, more electronegative, like instead of that being a methyl group on the right-hand side, if it was, or either one, doesn't matter, as long as it was an oxygen or chlorine, that's gonna change things, right, with the electronegativity?
And the size. But yeah, because when we look at those 1,3 diaxial interactions, if it's a chlorine that has a partial negative that's interacting with these hydrogens, well, these hydrogens, we don't usually show it. We consider it to be a non-polar bond. But these hydrogens do have a partial positive on them.
Yes.
So that's one of the reasons why chlorine, despite having an additional energy level and being bigger, doesn't have such unfavorable interactions as a methyl group. We go back to that table.
Yeah.
Chlorine was only a negative interaction of 2 kilojoules per mole, but a methyl group was up by 8,
Yeah.
despite the fact that chlorine is bigger by radius.
Okay.
So you're absolutely right that that's something that changes things.
Okay. So that, would that be considered then hydrogen bonding because of the partial charge on the hydrogen? Or, no, is that too broad?
It's an electromagnetic interaction. Or the shorthand for that, the electromagnetic is a little bit of a mouthful, called a Coulombic interaction,
Okay.
because Coulomb is charge, right?
Yeah.
If we did something like put another chlorine here, now you have 2 groups that are both big and both partially negative that are going to be pushing you against each other even more. So absolutely something that we're going to be watching out for, and that's going to affect things. It's technically, the official definition of a hydrogen bond means you need to have a hydrogen attached to something really electronegative.
Okay, so
So
that's
like,
why it happens with waters, to be honest.
exactly, because the oxygen's so electronegative. It's oxygen, nitrogen, fluorine, and chlorine, the big 4 for electronegativity. If you have a hydrogen covalently bound to any of those 4, you can have hydrogen bonding.
Okay. So carbon, not.
But a carbon attached to chlorine won't be hydrogen bonding by the technical definition.
Got it.
It has to do also with, yes, carbon is not significantly more electronegative than hydrogen, but it also has core electrons still. It's got you're talking about the second energy level that's not being shared equally, as opposed to hydrogen, which only has the first energy level. So when you pull electrons to the side with hydrogen, you're almost completely exposing the nucleus, which creates a really strong partial positive that way. Stronger than if you have a covalent bond between oxygen and carbon.
That makes sense. Okay. Yeah, that makes sense.
So what are your Tuesdays looking like now?
I've done after the lab, and
Okay.
I already feel better.
Good,
I slept great last night. And
Great.
the night before.
good. Just getting that change made
Yes.
makes a big difference
It really did.
on your stress level.
It really did, because after lab, I'm just beat. Because I'm already been here for 8 straight hours, you know?
Right, it's still a long day, but it's
It is.
manageable.
Yeah, that's reasonable, exactly, but I couldn't take it anymore after that.
You're not the only person at the college workload is an issue right now at all levels of staff at the college.
So I've heard.
So don't feel bad about needing to take your time back. Student first, right?
Yeah, I don't feel too bad, because those hours I would have missed, I stacked them on today, because we don't have labs, so it's way more manageable.
Plus, you're at the end of the week now, right?
Exactly.
You've got. Do you have anything on Fridays? No,
Just work.
just work. That's
Tutoring, and it's usually only the top students, because they get done at 9:50, and I start at 10.
yeah. So they come in, get some clarification on,
what they lectured on or
Yeah.
working on the homework for the weekend, or so they can enjoy their weekend as well. They're
Yeah.
doing chain roll right now. And I think tomorrow they're gonna do inverse trig derivatives. I think that's what they're doing tomorrow.
derivatives, I think I could still do. I might even, if you gave me an hour of prep time, I could probably even teach a lecture on chain rule. Don't make me do integrals.
See,
Integrals are hard.
they are harder, and and I'm glad I tutored because right now I get derivatives, like I get it.
Yeah.
I could probably teach a lecture on it
Yeah.
myself, with the limit definition as well.
Yeah.
Integrals are different.
Yep.
They're more complicated. And the tricks, that's what I need to work on. The one that gets me the most is partial fractions.
Yeah.
That's the one that gets me the most. I'm not the best with that.
I could do a little bit of integration. I can do some of the chemist and engineer tricks when it comes to not finding the real integral. I could get an answer for it. It wouldn't be in a way that Bruce or Larry would give me credit for it.
Okay.
But turns out when everything gives you, hundreds of data points per minute now, turns out that's the easier way to do it, is just do everything numerically. You don't have to do any of the integrals by hand and get a function for it.
Yeah. It was funny when we were doing the chem lab, we were doing graphs and we were asked to find the area under the curve. That would have been a gnarly one.
Yeah, those are not kind functions.
No.
But when you have when you have enough data points, turns out rectangle method works out just fine.
Perfectly, yeah. Speaking of those graphs, I was getting values into the thousands. That's reasonable, right? Considering how many data points there were.
Yeah, because we're looking at them relative to each other. Those numbers don't mean anything on their own because it's just signal versus time, right? So your units are in signal time,
Yes.
so which is useless.
Okay.
But it's proportional to the number of moles. So you can compare the area under curve 1 to the area under curve 2 and use that to find mole fractions.
Okay.
So area 1 versus area 2, the mole fraction of 1 is just going to be the area of 1 over area of 1 plus area of 2.
That makes sense. It's almost like the average.
Yeah, it's a lot like when we used pressures. We would say, okay, well, partial pressures, you can use partial pressures to find mole fraction because partial pressures are proportional to moles, right? Area under the curve is proportional to moles, so we can do the same thing. And getting that area is as easy as adding up everything from, make a bunch of triangles in here. I know this is more for Hannah since we were talking about this earlier. For Excel, you can make another column here next to signal. So if you have signal, and let me just pull it up here. We'll just do this as we're coming back. Let's see, did Carl email out the GC data from the distillation? Okay. And so let's see if I have a copy in here from last year. I probably do. GC data, it's probably that one. Yeah, that'll work. So if you want to take this so this has already got the data split up into columns, and it's already got a column added for volume versus instead of time. I took the time and converted it to volume. And I think this is data that I just made up, so it doesn't have the functions still in here. If you want to know what the area under the curve is, so first off, if we wanted to, I can't see, add a scatter plot for either of these, I'm just going to pick one. You guys know how to use Control-Shift in Excel, right? So Control and an arrow jumps to the end of data of that current data block, and Shift and an arrow selects things. So if I hold Control and hit up, it'll jump up to the top of the data and back, so I don't have to scroll the whole way. And if you hold Shift while you do it, you select it the whole way too. And then let go of Control and keep Shift down and push down once, and you'll get rid of selecting the header at the top. It's way faster than dragging the whole way down with your mouse. Oh, this is the volume. This is not the GC data. This is the fractional this distillation data. So I'm going to do the same thing here. Look at the heads for the simple. Probably can even let Excel, if I'm lucky, Excel will actually think properly when I do it. Yeah, Excel did it right. If I wanted to take this and find the area under these, you guys, those of you who had calc, remember the rectangle rule. When you want to find the area under a curve, you can approximate it by using a bunch of rectangles, which is where the definition of an integral came from. It said, okay, it's kind of like the definition of the derivative. The definition of an integral is, okay, you're going to find the integral under some function, x squared dx. Dx, change in x. So it's basically saying you're going to take the function and times it by the change in the x value, and that'll give you the area of a very small rectangle, right? If you add all those up, you get the area under the curve. Well, calculus will tell you how to do this by hand. You get the function that you could plug in. But if we have a bunch of data that doesn't look like nice, clean numbers, what we can do is, well, we have a dx. Our dx is our change in time. And our function is just signal. So we can actually make a column that and we can just call it the integral and say, and make it, okay, I'm going to say that my function is just going to be the signal. I'm not sure why it's fighting me. There it goes. And the change in x is going to be the current time minus the time from the data point before it. So you get a really skinny, tall rectangle, and that's the area of that rectangle. If we copy and paste that formula, we get a column that basically this is each of those, the size of each of those squares, and for the most part, they're not going to change that much until we get a big signal, which happened around 1 minute, right? So if I scroll down to about 1 minute, we get a big signal happening, right? If we want to know what the area under the curve is, we just add up all the boxes from time A to time B. So you can just go here and say, okay, I'm going to say that data point is the start of my peak. You hover over it, it'll tell you that is 57.4 seconds. And then, actually, no, sorry, that is the signal. It's 0.76. minutes. And we say the end of that peak is that one, which is at 1.105 minutes. You just add up all the boxes from 0.76 to 1.105, you get the area under that curve. So this is basically how engineers and scientists get around the fact that there are a lot of functions in nature that can't be approximated well with well-behaved continuous functions we could actually take an integral of. Differential equations is full of things we can define as being true, but we can't get an answer for them if we try to integrate. But if you get enough data points, you don't need a well-behaved continuous function that you can integrate. You just do this. It's not to say that differential equations is not immensely helpful. It's just being able to solve them is not nearly as important as mathematicians would have you believe.
So
is there a way to get like Excel to add all those points for you, or do you need to add them physically?
So you can actually, if I'm working with an existing thing, it's going to look a little bit weird. You can actually add another function, just say, call it the sum, and just say equals sum of this number to the same number. Actually, I want to hit F4 on the first one. And then colon C5. And when I copy and paste this is just going to give me a running sum of everything. And so you can actually just look at the sum at the end of peak 1 and the sum and peak 2. It'll look something like so our X values are going to be from here down, and our Y values are going to be these.
So just to be clear for this line, were we supposed to do just under the local maximums? The area under the local maximums? Because now that I'm thinking about it, I think I did the entire curve.
You can do the whole curve and compare it to, if you look at you just have to subtract off the stuff before that you cared about to get the area under one specific curve. So if you just looked at, let me move this into a, so if you look at what this function is, this orange line is the integral function. When you hit peak, it jumps, and when the peak falls off, it flattens out again. When you hit the next peak, it jumps again, and then it flattens out again. If we wanted to make this even more accurate, we could subtract off the noise. We could, so that it actually started at 0, and then it wouldn't be creeping upward. It would actually be more flat. That's the plus C term that winds up showing up in integration, right? We could basically subtract off this constant baseline to get a more well-behaved number. But basically, if you want to look at the relative size of these two peaks, you can look at the jump from here to here and look at what the jump is vertically and compare it from here to here. So just roughly, without even doing much math, I can look at it and say, well, these are close to the same. Their mole fraction is going to be close to 1. Or sorry, close to 0.5 for each of them. All right, and so there's ways we can clean this up when you're dealing with just one of these. And this is some of the stuff that you would learn when you go to a 4-year school. If you get a chance to do an undergrad research experience, they call them REUs, REU, research experience as an undergrad. basically a lot of what you do is you do the grunt work. Somebody else actually designs the experiments. Your job is just to run them and then take the data, clean it up, and then send them the figures so that they can actually do something productive with it. And so you would learn, that's where I learned a lot of these Excel tricks and how to integrate under a curve and how to subtract off the baseline, how to use control and shift with the arrow keys. Was when I was doing that in between my sophomore and junior year in college. And then I wound up doing the same thing again for junior and senior year. It was more fun the second time because I cared less. Turns out that I knew a little bit more about what was happening, and I knew enough to realize we weren't doing anything really that impressive. And so I just used it to study for my GREs and surf a lot.
So when I was doing this, I wound up playing with the data, so I could start an endpoint. Just to sort of have the results reflect what I was interpreting visually a little better. And really like not far past, it was like maybe a third of the way down that curve on the part right there, where I wound up cutting off to make it look, because otherwise it's just like, there's just a ton of butanol in there, like.
Well, and so really, if we had better, if we fine-tuned the GC a little bit and changed the ramp rate a little bit, in theory, we should be able to get it so that these two peaks are not overlapping. Because really, this first one, the acetone peak, is going to trail off in this exponential decay as well. So if you got your ramp rate slow enough, you crept up the temperature slow enough, and you had a long enough column, I think we're limited a bit by the GC we're using. The little tiny toy box is not a professional grade GC. But if we went slow enough, we could conceivably get these to separate out more, and then it'd be a lot more well-defined where one ended and the other one started. Because really, the butanone peak is actually reporting some of the acetone still, right? Because really the signal is giving you a little bit of both of them, because it hasn't fully gotten back to the baseline before the butanone starts. Right, so there is going to be some irregularities there because we're limited by our equipment a little bit. And if we were trying to publish this wouldn't be good enough. We'd go back, we would do it again, we would change the ramp rate, do the exact same thing until we could get it separated out more. And we might have to buy new equipment. Which is, one of the reasons why grants exist, right? We have this really promising idea. We just can't get things to work. We need a grant so that we can buy a new GC. And then when you get your new GC, lo and behold, everything works really nicely. And then you're able to publish, and that's kind of how the academic life cycle works. Find something cool that you can't study properly, get money to study it properly, publish on it, hopefully. Right, and then in the process, discover something else cool that you can write another grant for. When you're actually doing research in sciences, you're never actually just doing one thing. Your grant is funding, is sort of your day job. The thing is, research is both your day job and your hobby. So you have to have something else you're looking at on the side that gives you something you can write the next grant for, at the same time that you're putting in 40 hours a week just on the stuff that your current grant is paying you for. Which is a vicious cycle, because you wind up working 60, 80 hours a week most weeks, especially if you're the grad student. Not to discourage you, it's a very fun way, if you like science, it's a very fun way to spend your 20s. It just gets exhausting eventually if you're not getting enough reciprocation from your advisor, or your stuff's not getting published. It can get very depressing very quickly if you're spending in 80 hours a week on something that's never going to get published, and you're not going to pass your dissertation boards and things like that. So, but let's not dwell on that.
So
that was a little triggering.
Air hug, buddy.
No, it was great when I was in my 20s. I could handle that. And I just ignored my advisor. All right. If we want to look at cis and trans, or sorry, if we want to look at 1,3 versus 1,2, so this is 1,2 cis and trans. If we have 1,3 cis and trans, it's going to look a little different. So practice drawing your cyclohexane. Practice, okay, what is the cis version going to look like? If I have one methyl group up, if it's 1,3 and the cis, this one is also going to be in an axial position. Right, and that's a little bit easier to see. If we took this and we flattened it out, it's pretty clear both of the methyl groups are going to be on the same side of the ring, right? When it comes to this, a lot of times it's easiest to visualize where the axial positions are. And if you know where the axial positions are, you can kind of use process of elimination to say which one is the cis and which one's the trans. Right, so if I go through and I fill in all of the axial positions. Well, if I'm trying to draw the 1,2 cis, and I've got my methyl up here, if my choice is here or wherever the equatorial one is, it's pretty clear that the axial position on the second carbon is pointed in the opposite direction as this one, right? So that would make that the trans position, and then the cis position is going to be right there. So a lot of times it's easiest just to go through, figure out where the axial positions are, and then use that process of elimination to say where the equatorial is. And then you can figure out how to draw cis versus trans. So if this is the axial position on carbon 3, the equatorial position would look like this, coming straight out towards us. It's pretty clear that this is the bond that's going to be on the same side of the ring. It's not as obvious when this one's coming out straight towards us, it's not as obvious to say this is in the opposite position, that this is trans relative to where we started, but it's pretty clear that this is cis. So this one has to be the trans position. That's what I mean by using process of elimination. If you can see the easy ones, whatever is left has to be the other one. And so in this case, in this conformer, both of these are axial, right? Which is unfavorable. The other conformer, when we flip everything around, it's going to have a methyl group in the equatorial position, and this one flips as well. So it was in the axial position, now it's pointing straight out towards us. And if you're having a hard time seeing that, seeing where to draw it, remember, add the axial position first. Because the axial position is always going to be straight up or straight down. Then you can say, okay, well, this one's flat, this one's going back. The equatorial position must be right here.
So there's never going to be any, at least on the front side of this, there's never going to be any going into the board, correct? Because
Correct.
that would be into the structure
Correct.
itself.
Yeah, it's always going to be pointed, because these are still all tetrahedral carbons, right? We're still building on, this is all just Vesper geometry stuff, really. So you're still going to try and put everything in a tetrahedral shape where all of your bonds are pointed away from each other. The ones, and you're exactly right, the ones in the back are where you have something going away from us. Because it's this position, but going away. So it'd be one right there, going away from us.
Got it.
So if it's cis 1,3 dimethyl, We can have them both axial, or we can have them both equatorial. If it's the trans 1,3, the trans 1,3, we don't have it there. The trans position is going to put methyl group here first. Right, so you got one that's going to stick above the ring, and you got one that's going to stick below the ring if we flattened it out. Which means when we flip it, so it means we're starting with one axial, one equatorial, right? If we flip it, the axial turns into equatorial, and the equatorial turns into axial. So this is just like the 1,2 dimethyl in that one of these isomers is always going to have a favorable and an unfavorable, and the other isomer can have both favorable or both unfavorable. It's just flipped which one's cis versus trans because they point in different directions if they're not on carbon 1 and carbon 2. So for the 1,3 dimethyl, the more stable is not the trans, the more stable is the cis. Because that allowed us to have a conformer where everything was equatorial. All the big stuff. The hydrogens still have to deal with being axial. And you can kind of see that if you build the 1,3, if you flatten it out so you can see, okay, well, I definitely have, when you force these to be flat, they look a little bit like those, those lamb chops. My wife watches a lot of cooking TV. And you do those wraps of lambs, they tie to look like a crown. They look kind of like this. But you can see when I get it flattened out, this is my cis, because both of the methyls are on the same side. And when I put it into a chair conformer, we can have both axial or flip it, and you can get both of them to be equatorial. Right, so it takes some practice to be able to draw these consistently. And what we just did in figuring out which of the stereoisomers is more stable or which of the conformers is the most stable is exactly how test questions get asked, both mine and standardized tests. It's really easy to write a multiple choice question. Says, which of these following structures is the most stable chair conformer of 1,2 dimethyl cyclohexane? And then they give you 4 choices, 2 of which are not even the cis, 2 of them are the trans. And so then you can eliminate those right away because they're not cis or trans. And then you look at it and say, okay, well, of what's left, which of them is going to be more stable? It lends itself to writing multiple choice questions pretty easily because you have a finite number of options. You just have to know how to interpret those structures, especially when they're drawn like this without any of the lines being bolded. And you need to be able to look at this and see this, which takes some practice. All right, so this is going through an example where where it's chlorine and methyl, and looking at both possible conformers for trans 1-methyl 2-chloro cyclohexane. You could have both of the possibilities. You can either have them both axial or both equatorial. And again, without having the lines bolded, it's hard to see what's axial and what's equatorial here. So identify the axial ones first, because those are the ones that stand out. Those are the really obvious ones. Whatever's left must be the equatorial position. Axial is always going to be straight up and straight down. All right, let's talk about other versions of stereoisomers. So up to this point, we've been using the term isomer to mean specifically, we've mostly just been referring to constitutional isomers, where you actually have things, the connections between the bonds, between the atoms, are qualitatively different. So for instance, methoxymethane and ethanol, both the same formula, very different compounds, because you have different bonds. You have an oxygen-hydrogen bond for ethanol, but that you don't have for methoxymethane. Right, so these are constitutional isomers because you literally have different bonds. Stereoisomers are trickier because you have all the same bonds, just arranged differently in space. Right, so that's like our cis and our trans. Our cis and our trans is an example because it's still two methyl groups on cyclohexane. It's still all the same groups, but having one of the methyls up and one down versus having them both up is the difference, right? And that's what makes them stereoisomers. And we see the same thing as soon as we add, so anytime you have ring structures, you can have cis and trans, but also as soon as you add carbon-carbon pi bonds, or pi bonds of any type really, but especially carbon-carbon pi bonds. Because remember what pi bonds look like. So anytime you've got a restricted rotation, then you can have cis and trans. And so one way of restricting rotation is to make it into a ring structure. Because now you're not free to just rotate anywhere you want. The other most common way to see restricted rotation is a pi bond. Because remember, pi bonds look like unhybridized p orbitals that overlap with each other, right? So if you tried to take these two carbons and rotate them, you have to break the pi bond to do it, right? Because you have to disrupt this overlap in order to get it to rotate.
We can't do that before, I mean, I guess it could with other stuff, but those clouds are out of phase, right? So it would be very favorable, right?
Correct. Yeah, it's not going to be very favorable. You basically have to put in enough energy to fully break the pi bond in order to get it to rotate. And so that's where we're entering the gray area between the plasma at the center of the sun and Earth conditions in order to do that. You get it to a high enough temperature, you can break pi bonds at relatively mild temperatures, like 300 Celsius. So this is the sort of bond that on Venus might not actually hold. You might have free rotation if you were on Venus between these, because the surface temperature of Venus is like 300, 400 Celsius, that's a thing, somewhere around there. So on Earth, it's a hindered rotation either way. Hindered meaning it happens, but there's an obstacle. On Earth, we will consider cis 2-butene versus trans 2-butene to be two separate compounds. Whereas on a planet like Venus, they might just be considered conformers, because there are two different possible stabilities that you can almost freely rotate between. Right? So again, Earth-centric, which I think is fair. None of us are planning any trips to Venus soon. Soon, I mean. And so, but that means that these terms, cis and trans, apply to, we're going to use those in the nomenclature for any time we've got a carbon-carbon pi bond. And naming carbons or alkenes, so when you have a carbon-carbon double bond, is just like naming alkanes, just because it's on the board now, and then we'll get into chirality in a second. If you have a carbon-carbon pi bond, our rules for naming it are still the same. Our rules for naming it are still find your longest continuous carbon chain that has the pi bond in it this time. Now it's not just the longest full stop, it's the longest that has the pi bond. And name it with the same bases we've used before. If it's 4 carbons in a row, it's going to be bute. The difference is if it's got a carbon-carbon pi bond in there, it's not butane. It's not an alkane anymore, it's an alkene. So we just say it's butene instead of butane. We have to get a little bit more specific though, because we have to specify where the carbon-carbon pi bond is. It's not a branch, but it's still something that can be at more than one possible spot on butene. You could have one butene that looked like that. So we're going to specify where the carbon-carbon pi bond is, just with a locant, just like we've been practicing. So 2 butene versus 1 butene.
And you wouldn't say 4 because, or 3 because you want the lower number, right?
We want the lower number, and because by definition, an alkene bond has to be between 2 carbons, you don't need to say both numbers, because if you say 2 butene, you know that the other carbon is 3. You know it's between carbons 2 and 3. Right, so sometimes chemistry is funny in that they decide that we only need one number for this, but there are some other cases where we'll say both numbers, even though they're always going to be next to each other or something. For whatever reason with alkenes, we don't do that. Then the only other thing is, if you have a cis and trans isomer, you need to specify which version you have. If it's 1 butene, is there a cis and trans isomer? So cis meaning on the same side, trans meaning on opposite sides. If I blow up 1 butene to look at that pi bond, we have a carbon to another carbon pi bond. And on this carbon we have an ethyl group and a hydrogen. That's 1 butene, right? Is there a cis and trans version? There is not free rotation. But if I switched these, could I tell the difference? So anytime one side of your alkene is the same, then you don't have a cis versus a trans. Because if I flip this, it's not a different molecule. It's the same thing. If it's 2 butene, though, each of the sides of the alkene has 2 unique things attached to it. Now we can tell the difference. If we switch either one of these, we can't get back and forth between it. We can tell the difference. They can either both be up or they can be on opposite sides. Or they can both be down, but that would look the same as if they were both up, right? So this would be trans 2-butene. And the other possibility would be cis 2-butene. And if they were both down, if I drew both of the methyls down, that's the same as taking this molecule and flipping it like a pancake, right? The nice thing about carbon-carbon pi bonds is we know that this is planar now. That's easier to visualize, right? This is a flat molecule, at least this part of it's flat. So it's easy to visualize picking it up, flipping it over, and then you get both of the carbons down and both hydrogens up. So it doesn't matter whether you draw both up or both down, as long as they're both on the same side to make it cis. And on trans, they just have to be on opposite sides. There's one other type of stereoisomer, and this is one of the ones that's going to be one of the tricky things to visualize. So everybody grab a carbon, we have these right in front of us, and attach 4 different colored atoms to it. Doesn't matter if those atoms have other holes or anything like that, as long as you can tell the difference between them.
Bingo.
Bingo. All right. Now do the same thing, except make it the mirror image. So take the one in front of you and make it look exactly the same except the mirror image. So for mine, you can set it next to each other, it can be helpful for this. All right, while everybody else is still building. Now, Ryan, if they're set up like their mirror images,
Yeah.
take one of them and make it look like the other one. Try to put everything in the exact same spot. Oh, that's not a mirror image though.
Nope.
Look, your greens are in here. Switch your green and your blue.
Did I do this right?
Yeah.
Good job.
All right. So you've got your 2 mirror images. Take one of them and pick it up and try and spin it around in a way to make it look like the other one.
You can't.
You can't. No matter what you do, if I say, okay, I'm going to put my purple facing the same way and my orange facing the same way, but now my green and my yellow are backwards. If I make my green and my yellow work right, then my orange and my purple are backwards. And so that's the other type of stereoisomer is what's called enantiomers, and they refer to this concept as chirality. Chiral objects means that the mirror image of that object is not the same object. Right, so the example that gets used all the time is right hand versus left hand. And the reason why, the go-to example of why it matters is because you can't fit your right hand into a left-handed glove. You also can't fit a right-handed molecule into a left-handed active site on an enzyme. So they're not going to react the same way, especially physiologically, because so much of physiology and biochemistry is built around the 3-dimensional structure of proteins. Right, so a chair is non-chiral. If you take the mirror image of a chair, it's still the same thing, right? Nothing changed about it. If you take my extra special office chair that's missing one of the armrests, it's missing the left armrest. Now if you take the mirror image of it, it's not the same thing, because the mirror image would be missing the right armrest. And so, and that's the same example they're using here. Glasses, you take mirror image of your glasses, you get the same object, unless you have two different prescriptions. If your right eye is worse than your left eye, when you take the mirror image, you're going to have the prescriptions wrong, right? So anything that's got a right versus a left is chiral. Basically, in order for something to be chiral, you need 4 distinct sides arranged in 3 dimensions. The fact that we live in 3 dimensions, our brain processes in 3 dimensions spatially, is what leads to this. Because if you have 4 objects arranged in 3-dimensional space, 3 of them are going to form a plane, right? The 4th one can either be above that plane or below that plane. But you're limited. It has to be in one of those 2 positions. If it's not above the plane or below the plane, or if it's above the plane, and you try to make it below the plane, you have to flip the whole plane, right? Right, so for organic chemistry, the way we look at this is anytime you have a carbon that's tetrahedral, actually anything that has 4 distinct things attached to it, that you can tell the difference between those 4 things, then it's going to be a chiral center. Right, so here's an example, and it's a really kind of a cool example of something that seems, these 2 molecules look very similar, right? It's called R carbone versus S carbone. Those are what are called enantiomers. And so it's like that's the specific word meaning non-superimposable mirror images. R carbone is the smell of spearmint. S carbone is the smell of caraway. Seem like really unrelated smells, right? When I think of smell of caraway, I think of dill pickles. That's kind of the smell I associate with dill pickles. Good dill pickles, anyway. We actually did a lab when I was in OChem where we made both of these in equal amounts from a certain synthesis. Turns out it's hard to do that asymmetric synthesis where you favor making one version over the other. Most mechanisms you wind up making equal amounts of both, and then you can separate them later.
That's the oxidation of limonene, right?
I believe so, yeah. Oxidation of limonene. I think so, yeah.
Because I had drugs with limonene that eventually smell like spearmint and dill.
Right.
Because it's just degraded.
You can't really, so when you get a mixture that's 50-50 of these, it's really, really weird. You can't tell the difference. You can't tell whether you're smelling spearmint or caraway because you're smelling both. And that lab it actually confused my brain to the point where it took me about 6 months before I could tell the difference between those 2 again. I would smell spearmint gum and not be able to tell it apart from dill pickles.
That was an early COVID?
And that was pre-COVID, yeah. But very qualitatively different smells, not just in terms of the way we use those herbs, but the only difference is one's the mirror image of the other.
Question on that.
Yeah.
One of them's going in, the other one's coming towards?
Yes. So, and again, if we're trying to figure out whether or not something has an enantiomer, look at all the carbons and see if there are any carbons that have 4 distinct things attached to it. So this carbon has this group here. It has this ring structure, and it has a hydrogen that's not drawn. So the hydrogen's coming out towards us on this one. This ring structure seems like it's the same object, but you can tell the difference between did I go left or right when I go around the ring, right? It's 1, 2, 3 bonds to the oxygen. If I go one direction, it's 1, 2, 3, 4, 5 bonds to the oxygen if I go the other way. So the fact that you can tell the difference, which direction around the ring you means that those 2 bonds are attached to different things, even though they're technically attached, they're both attached to a ring. Right? The fact that the ring has two distinct directions means it's two distinct substituents attached to that carbon. Amino acids, another good example. Amino acids have a carbon in the middle that's attached to an acid group, an amine group, a hydrogen, and an R group. 4 distinct things, right? Our body only uses one version of these amino acids. It doesn't use both enantiomers. Basically for the same reason that we don't use both right-handed and left-handed screws. Screws are enantiomers, are chiral as well, which is why righty-tighty, lefty-loosey, right? If everybody just went to the hardware store and picked whichever version they felt like that day, it'd be really, really hard to build things and take things apart, right? Am I using a right-handed screw or a left-handed screw? Well, that's exactly why our bodies evolved to only use one version, because otherwise it just gets confusing. No, I need a right-handed alanine, not a left-handed alanine. I mean, it effectively doubles the number of amino acids you could use, but at the same time, it doubles the number of amino acids you need to have on hand. And if you switch that, all of a sudden they don't link up into binding sites the same way. If you put your R group in the same position, but you switch these others, you can't align them in such a way that you can put them in the right binding sites. Which is exactly why R carbone smells different than S carbone, because it's the same idea. Those molecules in gas phase are hitting receptor sites in your nose. And if they fit to the receptor site well enough, it sends a chemical or an electrical signal to your brain saying, hey, we got a positive over here. And the part of your brain that gets fired up tells you what it smells like. Does it smell like this or that? So really, smell and taste is actually your brain's way of testing the chemical structure of everything around you. Anything that fits into the right receptor sites sends a signal to your brain, and depending on what receptor site you hit, you get different scents and tastes. It is cool. Just like your eyes are your brain's way of estimating the wavelength or the energy of photons. Okay, our senses are really our body's way of interacting macroscopically with the microscopic quantum world. For the most part, even touch, you're not actually touching things, you're actually feeling the electrical repulsion from the electron clouds of whatever you're touching. The electrons in the speaker are pushing back against the electron clouds in my finger, which, if it pushes enough, sends a signal to my brain and says, hey, your finger's touching something.
So what is it about COVID that messes with your receptors and makes it so you can't smell?
I have not the faintest clue. I do know that brain damage can do that. I had a wrestling coach in high school who, I don't know if it was a car accident. He used to be a construction worker, and I think he got something dropped on his head. And when he recovered from it, he lost his sense of taste and smell. He never could smell or taste again. Still drinks Coors Light though, because he remembers he liked it before he had his accident. If you got no sense of taste, it might as well be Coors Light, right? But yeah, so I know it's tied to, you can damage things in your brain by doing that. And it's not that your nose no longer works, it's that your brain doesn't know how to interpret things. Basically, the signal gets lost or mixed up. There's other cases of brain damage where we wind up with what's called synesthesia, where all of a sudden you wind up with a scent that actually fires more than one sense when it gets to your brain. Instead of when you smell something, it also triggers the color aquamarine. Or when you hear a certain word, it triggers the smell of vanilla. So something about the way your brain processes your perceptions, your senses, signals can get mixed up when you have brain damage or when you have certain infections. And that can cause things to be weird for you relative to everybody else.
Do you know why Jeffrey pine smells like vanilla?
Those are sugar pines. Sugar pines smell like vanilla because they actually make vanillin, the same compound that gives vanilla its scent. Sugar pines actually produce that in their pine cones to small amounts. So that's, yeah, it's a lot of pines also make other aromatic compounds that will smell specific way, and a lot of hops do the same thing, which is why you can have beers that smell like citrus despite the fact there's no citrus in it. Or you can have hops that smell really piney, or you can have weed that smells really skunky, right? There's a lot of similarities and overlap between some of these aromatic compounds that different organisms make naturally. All right, anybody think of two other 3D objects from the macroscopic world that are chiral? Chiral means that the mirror image is not the same object anymore. Your hands? You can go microscopic if you wanted. I was thinking macroscopic. What'd you say, Ricky?
There's that faucet.
There's the faucet. Yeah, the faucet it has a front, back, top, bottom, 4 distinct sides, right? If it didn't have this faucet here, or if the handle was right here, it wouldn't be chiral. But the fact that you have 4 distinct sides of it makes it so that, okay, when I'm looking at it head on, the handle's on my left. The mirror image, the handle would be on my right.
Same thing with the tripod and the handle.
The tripod and the handle?
Without the handle, it would be, though, right? The door.
The door. Doors, doors, I don't know if any of you have ever installed doors before or ordered doors. You have to make sure you order the right chirality. If you order a right-handed door for a left-handed door frame, you're going to wind up with your door opening the wrong way, and you walk in facing the wall instead of facing the room. Doors are absolutely chiral. Yeah.
I think the sides have to be even.
The what?
If you have an odd number of sides, you can get it to be the same.
If it has 5 sides that are different, I think it's more than 3.
More than 3?
Whether it's odd or even, it has to be more than 3. Because if it's 3, then you can just define a plane, right?
Yes.
And flip it whichever way you want.
Yes.
But if it's 4, all of a sudden you have to define a plane and have something above and below it.
Yes.
And 5 is the same thing. Cars are another good example. Take a mirror image of your car, you get the British version of your car, right? Steering wheel on the wrong side. All right, we're about out of time. I will double check the quiz to make sure it doesn't get to assigning priority or naming the enantiomers. But this, I think you could do. Identify all so asymmetric centers are atoms that are chiral. Atoms that are attached to 4 unique things. So on this molecule, you can go through, and anytime you find something that has 4 distinct things attached to it, even if not all of them are drawn, a hydrogen still counts, a lone pair still counts, because they still take up space around that tetrahedral atom. So going through this, you should be able to find 1, 2, 3 asymmetric centers, 3 chiral atoms in here. And so that carbon very obviously is attached to 4 different things. Not as obvious, but so is that carbon. No, I miscounted. I counted the nitrogen, but the nitrogen has 2 methyls, and the 2 methyls are identical. All right, so as soon as 2 of those 4 things are the same or are identical, then it doesn't work anymore. If you replace one of these with another hydrogen, now all of a sudden the mirror image is the same because you can twist it around. You have those two hydrogens that you can't tell the difference between, make all the difference in the world. All right, so quiz will be on some of this, some conformer stuff, looking at cyclohexanes, and we will get into naming these on Tuesday.
Okay, to hold on these for the weekend, or you want?
Yeah, go ahead and hang on to those. Brad, what number is that one?
5.
Okay, that's right.
That last molecule you had up,
Mhm.
how would you go about naming that? Or is that, have we not gotten there?
You wouldn't.
You wouldn't?
If it's a molecule that matters, then it's going to have a common name.
Okay.
Otherwise, you're going to start from having a common name and then modify it.
Got it.
Like this can be considered a propanoate group. So you can name all of this with the prefixes as propanoate attached to it. All of, that's an amino group, a dimethyl amino group. These benzene rings, you can use prefixes for those. You can build out an IUPAC name for it, but it's going to get pretty unwieldy.
Okay.
So probably, this is either a molecule that I just made up, or it's something that specifically that has some biological purpose and therefore will have a common name.
It looks sort of like Benadryl, but it's not.
It's not Benadryl, but it does look a little, the nitrogen with the two benzene rings makes it look close to Benadryl.
And then there's, well, it's acid group, it looks like sort of the ether group.
Yeah.
I was just curious, because I was looking at it and I was like, well, where would I start? Would I start with rings? Like, which one?
You go, so you basically, just like we talked about with the alkenes, you find the most important functional group and you name it according to that. And you say, okay, this is my parent molecule. And then you just start throwing prefixes at it. And we'll just start adding new ways to do prefixes to handle other functional groups and benzene rings and stuff like that as we go.
It's addressing your, scientific thing. Vanillin is like a breakdown product of software lignin. Lignin is software.
Okay.
So like, it has like the same functional groups that are on vanillin, which is like hydroxy and methoxy.
Which is why you can get certain whiskeys that are, if you age it in the right wood, you can get like notes of vanilla.
Is that why my J-Lo tastes a little bit like vanilla?
Is that why what?
J-Lo tastes just a slight.
Yeah, actually. Yeah, it's the wood that they're using, and it has a little bit of a compound that's similar enough in structure. It might not actually be vanillin, but then again, it might be vanillin.
Well, that's the thing, with pyrolysis products. 'Cause
Yes.
They'll scorch the barrel. And
Right, that's true.
so then you are actually, yeah, vanillin is, as well as other aromatic compounds. Good luck.
You got it, you
I
got it.
also get smoke.
Very fine.
I will.
From,
Well,
this is actually kind of a cool thing structurally, where you look at this if you pull that aldehyde group off of vanillin, you have this called Y